What is going on, everyone? Welcome back to another tutorial. Today we're going to be doing a Fluent tutorial, which is the flow through two concentric rotating cylinders. Let's get into it. So as I mentioned, the analysis that we're going to do is analyzing the flow through an annulus that has two rotating cylinders with heat transfer through its walls. We can see a diagram to the right of what this looks like. So we're going to have two cylinders here, and we are going to be analyzing it in 2D. So we're going to be taking a cross section of this geometry. We're going to have a fluid, which is going to be specified as water between our two cylinders. And the density is going to be set at 998.2 kilograms per meter cubed, and the viscosity is going to be set at 0.001003 kilograms per meter second. And these are properties that are specified for water in Fluent. For our geometry, we're going to specify the outer cylinder to have a diameter of 300 millimeters and the inner cylinder to have a diameter of 200 millimeters. The wall thickness is going to be set at 1 millimeter for each of the walls of our cylinders, and this is going to be important for the heat transfer component of the simulation. And for boundary conditions, we're going to initialize the outer wall to have a velocity of 25 rads per second in the clockwise direction, and the inner wall to have a velocity of 50 rads per second in the counterclockwise direction. Similarly, for the temperature, we're going to initialize the outer wall to have a temperature of 300 Kelvin and the inner wall to have a temperature of 310 Kelvin. And by setting up the simulation, we'll be able to see how the flow of water is going to react between these two cylinders. So knowing our dimensions for the geometry and the boundary conditions that we need to set up, let's go ahead and jump into Workbench and start working on this simulation. Now with Workbench open, we can go ahead and start building the simulation. In the middle here, I have my project schematic. This is where I'm going to be building the simulation. And on the left-hand side here, I have all of the analysis systems that I could use. But for this particular simulation, we are going to grab the Fluid Flow Fluent module and drag it into our project schematic. And the first thing that we're going to do is build the annulus that we're going to be analyzing the flow through. So let's double click on geometry. And in the bottom left-hand corner here, it says starting SpaceClaim. So I'll wait for that to load. Now with SpaceClaim open, we can go ahead and start building the geometry that we need for the simulation. Since this is a CFD simulation, the geometry that we're going to build is going to represent wherever there is fluid within the simulation, meaning the space between the two cylinders. So to get started, let's press on End Sketch Editing because by default, ANSYS has us sketching on the ZX plane, but it's just better to sketch on the XY plane because it's easier for initialization later on. So let's go ahead and press on End Sketch Editing. And we're going to re-enter sketch mode by pressing on the pencil here. And I'm going to choose the plane that I want to sketch on. So I'm going to choose the XY plane. I'm going to press on the Z axis here to make this normal to the screen to make it easier to view. And I'm going to choose my circle command here. I'm going to snap it or click it on the origin of the environment. And I'm going to drag out the circle. And as you can see, we have a little dimension marker that appears. So I can input the first dimension of 300 millimeters, which represents the dimension of our outer cylinder. There we have it. And since we have the circle command already selected, I can go ahead and make the inner circle as well. So snap it to the origin of the environment, type in 200 millimeters, press enter, and there we go. Now we have two cylinders. And if we press on End Sketch Editing, it will create a surface between these two sketches. And the surface here that we've built represents the fluid that we have inside the two rotating cylinders. So that is it for the geometry for the simulation. So we can go ahead and close SpaceClaim by pressing on the X here. And now we can see that we have a check mark beside geometry, so that is ready to go. Next up will be the meshing stage. So let's double click on mesh. And down here it says starting meshing, so I'll wait for that to load. Now with the mesher open, we can go ahead and start building the mesh for the simulation. A well-built mesh will allow ANSYS to effectively do the necessary calculations over very small increments over the geometry that we created, which will allow it to determine the solution that we ask it for. But to start building this mesh, let's go ahead and generate the default mesh that ANSYS will create for this geometry. So to do this, let's go ahead and right-click on mesh and press on Generate Mesh. And as we can see, the mesh that ANSYS has created is very, very coarse, and a lot of the elements are very skewed and not very orthogonal to one another. So we can definitely do better. So let's add a sizing to this mesh in order to refine and make the elements smaller. To do this, we're going to right click on mesh. We're going to go to insert and insert a sizing. As you can see, we have two yellow fields down here. This is information that ANSYS needs from the user in order to handle the sizing correctly. So to start, let's define the geometry. We're going to go ahead and press on the edge selector tool up here. We're going to select the two edges of our surface, the inner edge, and holding control, I'll select the second edge. Then I'm going to go ahead, and as we can see, both of them have been highlighted. So I'm going to go ahead and press on no selection and press on the apply button that appears. And we can see that two edges have been added to the geometry for this sizing. Next up, for the definition in type, I'm going to go ahead and press on element size. And as you can see, a little triangle appears here. I'm going to use this drop-down menu and click on number of divisions. And for number of divisions, I'm going to select 300. And what this is going to do is it's going to break up each of these surfaces into 300 elements. So there's going to be the face or the edge of 300 elements on each of these surfaces, as you can see by the little yellow dotted lines that appear. So let's go ahead and regenerate the mesh. Right click on mesh and press on generate mesh. As you can see, the mesh is a lot more refined now and will be able to capture a lot of the smaller details and behavior of the flow within the annulus. We can see that the elements along the edges are pretty orthogonal, but as we move to center, the elements get much bigger and become less orthogonal, less square. So we can definitely do better than this as well. So let's go ahead and add a face meshing in order to control the shape of the elements. To do this, we're going to right click on mesh again. We're going to go to insert and press on face meshing. For face meshing, we need to define the geometry that we want to add the face meshing to. So we're going to go ahead and use the face selector tool. As we can see, it's already selected. And I'm going to go ahead and press on the face to highlight it, and I'm going to apply it to my face meshing. In the definition here, we can see that the method is quadrilaterals. So this will help control the shape of the elements that the mesh creates and hopefully make them all quadrilaterals that are fairly orthogonal. So let's go ahead and regenerate the mesh, right click on mesh and press on generate mesh. Now that we've regenerated the mesh with an edge sizing and a face meshing, we can see that the mesh that ANSYS has created is a lot more refined and the elements a lot more orthogonal than the other meshes that it created before. We can also go ahead and check the quality of the mesh by going to the quality tab here, pressing on the plus. And for the mesh metric, we can go ahead, press on none, and choose element quality or orthogonal quality is a better one. And as you can see, we have a little chart that appears down here that shows the number of elements and how orthogonal the elements are. And we can see that all the elements fall within almost 100% orthogonality. As we can see in the drop-down menu here, we can see that it's not quite equal to 1, but it is very close. If we go ahead and press on the columns, the yellow columns of our bar graph here, it will show the elements in each of the categories here, which show their different levels of orthogonality. So if we go ahead and press on the last column here, these are our most orthogonal elements. And if we press on the first column here, these are our least orthogonal elements. But as we can see here, on average, this mesh is very orthogonal, so it's going to be good to go for our analysis. Next up, we're going to add some name selections for the geometry that we've created, and this is just going to make it easier and Fluent to initialize the boundary conditions. So let's go ahead and press on none so we can see all of our whole mesh here. And let's use the edge selector tool by pressing on the edge selector tool here. And let's press on the first edge. Let's right click and go to create name selection. And we're going to name this inner wall. Press on OK to confirm the name selection. As you can see, there has been another branch of the project tree here called name selections. And if we press on that, we can see that we have inner wall as a name selection. And as we add other name selections, they're going to appear on this branch here. So let's add another one. Let's go ahead and using the edge selector tool again, let's create the outer wall. So left click on the outer edge, right click, go to create name selection. And we're going to go ahead and name this outer wall. Press on OK. And I'm also going to create one for the fluid flow or wherever we're going to have fluid within our domain here. So let's use the face selector tool instead. Let's choose the face, right click, go to create name selection, and we're just going to call this something like fluid domain. Press on OK. And now we have all of our name selections here and we have our mesh created. So we can go ahead and go back to the Workbench and launch Fluent to initialize the model, boundary conditions, and run the simulation. So let's go ahead and do that. So now that we've returned to the Workbench, we can see that we have a lightning bolt beside mesh. To move on to the next stage, we need a check mark. So why has this happened? Well, this has happened because we made changes without updating the entire module itself. It still has all of the information that we inputted, such as the name selections and the different elements that we added to create an orthogonal mesh, but we need to update the module. So to do this, I'm just going to go ahead and right click on mesh and press on update. And then this is just going to ensure that all the information that we initialized in the meshing stage is going to be sent to the setup of the simulation. So now that we've updated the mesh and sent all the information, we can see that we have a check mark beside mesh, and we can now launch Fluent by double-clicking on setup. Upon double-clicking, we're met with the Fluent launcher. For the simulation, we have the dimension as 2D, so that is good. We're going to use double precision for this simulation, and for the solver processes, I'm going to put this to 2. And in parallel settings, for GPUs here per machine, I'm going to put it to 1. And this depends on the machine that you're running ANSYS on. This will just allow the simulation to run a little faster. And these are pretty generic numbers for any computer that you're using. So you could go ahead and use these as well. Now with this initialized, we can go ahead and press on start to launch Fluent. So down here in the bottom left, it says starting Fluent. So I'll wait for that to load. Now with Fluent open, we can go ahead and start initializing the boundary conditions. For good practice, it's always good if we check the mesh during this stage as well. So if we go ahead and press on the check beside mesh, in the console window here, it prints out a whole bunch of information about our mesh. And as you can see, the minimum volume and maximum volume and total volume, they're all positive numbers, so that is good. If ever you were to see a negative value for one of the volumes of our mesh elements, that would be not good because it's physically impossible to have a negative volume. So you would have to go back to the meshing stage and fix the mesh that you've created. In Solver here, let's leave all this information the same, but in models, if we double click on models, for the viscous model, I'm going to go ahead and choose laminar from the window that appears here and press on OK. And also, since we have heat transfer in this simulation, I need to turn on the energy equation. So to do this, I'm going to double click on energy, and I'm going to put a check mark beside energy equation to enable energy equation. So that is good for my models. Next up, let's add the materials that we want to use for the simulation. To do this, I'm going to press on the plus beside materials, the plus beside fluids, and let's double click on air. So air is the material that by default is already in ANSYS. By double click on air, we can see that this window has appeared here with all of the properties for air. But if we wanted to add another fluid for our domain, let's go ahead and press on Fluent Database. And this is going to open up all the different fluids that are available within Fluent. And if I scroll down to the bottom, let's go ahead and choose water liquid, as this is the material that I wanted to use as specified from the problem statement. And these are the properties that it has here. So to add it to the project tree, I'm going to go ahead and press on copy. And as you can see in the materials and fluids, water liquid has been added. So that is good to go. So we can close all of these windows now. Next up is the cell zone conditions, and this is just initializing the fluid domain with the right material. So let's go ahead and do that. I'm going to double click on cell zone conditions. And as you can see, we have fluid domain. This is a name selection that we created during the meshing stage. So if we press on fluid domain and press on edit, we can see, first of all, the type is a fluid, not a solid, so that is good. And if we press on edit, this opens up this window here, and you can see that by default, the material is air, but we want water since we've added that to our project tree. So we can go ahead and choose water instead. Press apply, and now press on close. So now water has been initialized for our fluid domain. We can also go ahead and add the boundary conditions for velocity and temperature. So to do this, I'm going to press on the double click on boundary conditions. And as you can see, we have our other name selections that we've created. Interior fluid domain is one that was automatically generated by ANSYS. We don't have to worry about that one. The ones that we do have to worry about are the inner wall and outer wall. So let's go ahead and click on inner wall. And as you can see, the type is wall instead of other types of boundary conditions that we have, such as inlets and outlets. So for this inner wall, we want the type to be wall. And if we press on edit, this opens up this window here. By default, the wall is stationary, but we want it to be moving. We have a rotational speed to initialize. So let's go ahead and press on moving wall. This is going to open up this window here. We know that the velocity of the wall is rotational, so let's go ahead and press on rotational. Since this is a 2D simulation, we see that the rotational axis origin, there's no Z axis available for us in this tree here. That is okay because we sketched the geometry to be on the XY plane. So the rotational velocity direction would be in the Z axis. So that is already handled by ANSYS. So we don't have to worry about initializing that. And we can see we can also implement a magnitude for speed in rads per second. So we need to make sure that the speed from the problem statement is also in rads per second, which it was. And we're going to implement for the inner wall, it had a speed of 50 revolutions per second in the counterclockwise direction. So by default, counterclockwise is positive. And if we want to specify a velocity in the clockwise direction, we would input a negative here. And we're going to see that for the outer wall. For thermal, if we press on the thermal tab, this is where we can specify the boundary conditions for heat transfer. In the problem statement, we specified a wall thickness and a temperature for our wall. So let's go ahead and press on temperature. From the problem statement, we define the temperature of this boundary to be 310 Kelvin. So let's implement 310. And the wall thickness in meters was 0.001, which represents 1 millimeter. And we don't want any heat generation for this wall. We just want it to be steady at 310 Kelvin. So we can go ahead and press on apply. And we can close this window. So now inner wall has been initialized with its velocity and temperature. And we're going to go ahead and do that for the outer wall as well. So let's click on outer wall. We need to make sure that the type is wall. That is good. Let's press on edit. This opens up this window here. We have a moving wall that has a rotational velocity. Rotational axis is in the Z direction. And it had a speed of negative 25 rads per second. And again, the negative here is specifying the clockwise direction. For thermal, if we click on the thermal tab, let's go to temperature. And in the problem statement, we specified this boundary, the outer wall, to have a temperature of 300 Kelvin, so that's good. And again, the wall thickness to be 0.001, which represents 1 millimeter. No heat generation, so that is good. Press apply. And now we can close that. So now we've implemented all the boundary conditions that we need for this simulation. Next up is specifying the method that we want to use for solving this simulation. So let's go ahead and press on methods here. Double click on methods, sorry, and we can see that the scheme is coupled. This is going to be the method that we're going to use for the simulation, since the scheme is very stable. We could use pretty much any of the schemes that come in the drop-down menu here, since this is a very simple simulation. But let's go ahead and leave it to the coupled scheme because it is a very stable scheme to begin with. Next up is ensuring that our residuals are good. So we want to make sure that the solution is going to converge to a value with high accuracy. So to do this, I'm going to press on the plus beside monitors, and I'm going to double click on residuals. And we can see the absolute criteria for all of the residuals is 0.001, except for the energy, which is 1 e to the negative 6. But I'm going to make this the residual for all of them just to get slightly better accuracy for this simulation. Press on OK. So that is good to go. Next up, we can go ahead and initialize the simulation. So to do this, I'm going to go ahead and press on initialization, double click on initialization, sorry, and we're going to use the hybrid initialization method for the simulation. So click on hybrid initialization and press on initialize. And in the console window here, we can see that it says hybrid initialization is done, so that is good to go as well. Next up is actually running the calculation for the simulation. So let's go ahead and press on run calculation, double click on run calculation. And for the number of iterations here, I'm going to put 500. This should be enough to get the convergence that we want. And let's go ahead and press on calculate. And as we'll be able to see in the console window, it will start writing all of the iterations that it does. And in the top here, instead of seeing our mesh, we should be able to see our residuals graph over the iterations that Fluent will perform. And what we want is the residuals to drop below the specified values that we did in the monitors. So as this simulation is loading, I'll cut to when it is finished. Hey guys, welcome back. We can see that the calculation is now complete. So let's go ahead and press on OK and see what happened. If we go ahead and look at the scaled residuals here, we can see the graph of the residuals over the iterations. And as we can see, the simulation ran through all 500 iterations and the residuals didn't drop below the convergence values that we wanted. However, we can see that the residuals did stabilize to a value, meaning that the solution did converge to some results. So let's go ahead and check the results and do the result validation for this simulation. So let's go ahead and move on to CFD-post. So I'm going to go ahead and close Fluent by clicking on the big X. Are you sure you want to quit this application? That is okay. And now it's going to do its exiting phase. Now that we've returned back to Workbench, we can go ahead and launch CFD-post to view the results that we got. So let's double click on results. As you can see in the bottom left corner here, it says starting CFD-post. So I'll wait for that to load. Now, if CFD-post open, we can go ahead and start viewing some results. Let's press on the Z-axis here to make it normal to the screen. And there's several things that we can do. We can make streamline plots, vector plots, contour plots. It's really up to you what you want to see as the user and what variable you want to show. But for results validation, it's always good to ensure that we analyze the behavior that's happening and ensure that the boundary conditions are being respected that we put into place. So let's go ahead and check that. The first thing I'm going to do is create a vector plot. So I'm going to press on the three little arrows up here that says vector. This is going to insert a vector plot. I'm going to press OK. You can name it whatever you want. For the location of this vector plot, I'm going to press on symmetry 1 or symmetry 2. It doesn't matter. You can choose any of these. And for the variable, I'm going to show velocity, so that is good. I'm going to go ahead and press on apply. As we can see, we have a whole bunch of vectors that pop up based on the direction of the velocity and the velocity magnitude for the solution that ANSYS calculated. If we wanted to make the symbols a little more visible, we could do that as well. Let's go ahead and press on symbol, and for symbol size, let's go ahead and put in 2 to make the symbols a little bit bigger. Press on apply, even 3. Let's change that to 3. Press apply. Okay, so they're a little bigger now. If we zoom in, let's zoom into one of the sections of our graph here. And let's, instead of a line arrow, let's use a 3D arrowhead. It might make it a little bit easier to view. Here we go. So as we can see, the velocity on the outer wall is going in the clockwise direction, so that is good, and the velocity on the inner wall is going in the counterclockwise direction. So those are respecting the boundary conditions that we put into place, so that is good. And as we can see throughout the fluid within the annulus, there is a changing in fluid direction. So as we move away from the inner wall, due to the effects of the rotating wall in the clockwise direction, we can see that the fluid from the inner wall slows down to a velocity of basically 0 and then switches directions to match the velocity of the outer wall. We could make this a little more visible by going ahead and plotting a contour plot instead. So let's go ahead and do that. I'm going to zoom out a little bit. And for my contour plot, I'm going to press on the little colorful map that I have up here that says contour if we hover over it. And for the name, you can name this whatever you want. I'm just going to name it contour 1. And for variable, I'm going to go ahead and show the velocity. And for location, it's going to be symmetry 1 again. And for number of contours, this just specifies how many colors we want in our plot. The more contours that you add, the smoother the gradient is going to be within the colors of the plot. So I'm going to put 20 for number of contours, press on apply. And I'm going to go to the project tree here and deselect the vector plot so that we don't have the vectors showing up anymore. And as you can see, this is our contour plot for the velocity for this simulation. And it shows a similar story to the vector plot that we plotted before. As we can see, the velocity of the inner wall is specified to be 5 meters per second. So this is specifying the tangential velocity of the inner wall. And similar story to before, the velocity of the fluid slowly decreases as we move away from the outer wall and eventually changes directions to match the velocity of the outer wall. One thing to note about this contour plot is it doesn't actually show the direction of the velocity, so we only have the magnitudes of the tangential velocity shown here. We could also go ahead and change whatever variable we wanted to see. So if we want to see velocity in the x direction, velocity u, we could go ahead and show that, press on apply. And now we're only showing the velocity of the fluid in the x direction. So that is how to create contours and how to show different parameters that you would want to see. And finally, I'm going to show you guys how to create a velocity distribution graph if you wanted to show the velocity distribution along a section of this annulus here. So to do this, I'm going to go ahead and press on location up here, and I'm going to insert a line. This is going to be named line 1, so that's fine. So to create this line, we're going to specify 2 points. And I'm going to specify one of the points to be on the inner wall and one of the points to be on the outer wall. And since I created this geometry at 0, 0, I know what the dimensions of these 2 points are going to be. In SpaceClaim, when we built the geometry and in the problem statement, we specified the geometry to have a dimension of millimeters. But note that in CFD-post here, we have a different unit, which is meters. So we can't just input the points to be in millimeters. We need to actually use the location of the points in meters. So with our geometry created at the origin and with an inner diameter of 200 millimeters, we know that the radius is 100 millimeters or 0.1 meters. So for 0.1, I'm going to go ahead and put 0.1 for the x, and I'll leave 0, 0 for 0 in the y. So this is going to be on my x-axis. So it should be located here. And 0 since the geometry is 2D and we don't need a z coordinate. And my point 2 is going to be on the outer wall. So I'm going to leave the y coordinate to be 0. So we're going to make the line along the x-axis. And again, z coordinate 0 because it is a 2D geometry. And for the x-axis coordinate, I know that my outer diameter was 300 millimeters. So at the origin, this gives me a radius of 150 millimeters or 0.15 meters. So now with my coordinates for my start and end point of my line put into place, I can go ahead and press on apply. And if we deselect the contour, we can see that we have a line that has been created on our geometry here. And we can see that it's a little bit slanted, but that's because my coordinate axis is not exactly flat here. It's a little bit rotated to the clockwise direction. So now to make a graph of the velocity distribution along this line, let's go ahead and press on the graph icon up here. This is going to be named chart 1, so that is good. For title, we can name this whatever we want. We're going to call this velocity distribution. The type of plot is going to be a line. You could choose different types of plots depending on how you want to plot the data that you collected here. For data series, let's go ahead and specify the location. So the location that we want to show the velocity distribution on is the line that we created. So if we press on the drop-down menu, we can see that we have line 1 here, which is the line that we've created. So for x-axis data, we want to specify the length of the annulus or the length between the inner and the outer diameters or cylinders. So for the variable, I'm going to go ahead and choose x to specify the position. And in the y-axis here, we want to see the velocity distribution. So for variable, I'm going to choose velocity. And we could go ahead and change the line display and chart display if we wanted to. But by default, it should generate a pretty good chart. So let's go ahead and press on apply. And now in the window here, we can see that we have the velocity distribution graph for the velocity in the radial direction. If you want to export the data that you've collected here, you can go ahead and press on export and then put it in a file folder where you wanted to. And if we want to show another graph, we could do that as well. To make a second graph, you have to go ahead and press on the graph icon again. If you just change the values in here, it's just going to overwrite the graph that it's showing you. So here we're inserting another chart, which is chart 2. We're going to create another line chart, and for the title, we're going to call this the temperature distribution. We're going to create an XY line type plot, and in data series, we're going to select the line which is in the radial direction again. For x-axis, this is going to be the position in that direction, and for y-axis, we're going to show the temperature distribution by selecting temperature. Go ahead and press on apply. And then in the window here, we can see that we have our temperature distribution in the radial direction. And this further validates the results that we got, because we can see that at the inner wall, we have a temperature of 310 Kelvin, and at the outer wall, we have a temperature of 300 Kelvin, which is respecting the boundary conditions that we put into Fluent. So now that I've shown you guys how to create different types of contour plots, vector plots, and distribution charts in some direction, you could show whatever variables that you guys need to show for your simulations. And with the results validation completed, we could say that the simulation was completed successfully with a good degree of accuracy. So that will be it for this simulation. Don't forget to like the video if you guys thought it was helpful, and subscribe for more engineering content.